Hello, everyone. Good morning or good afternoon, depending on your location. This is Brooke Akins, and on behalf of Q1 Productions and IBA Industrial, I'd like to welcome you to today's webinar and thank you for joining us. Today's course will discuss the different X-ray solutions, and we'd like to thank IBA Industrial again for sponsoring today's webinar. We're very lucky to have two speakers from their team today, Mr. Frederic Dessy, who's the product manager, as well as Jeremy Brison, Director of Product Management and Innovation. And again, they'll be presenting on different X-ray solutions and how to put them into practice. Please note that a copy of today's presentation recording will be sent to all registered attendees upon completion of today's webinar, and it will be made available at a later date on the IBA Industrial YouTube page, so please feel free to check back there. We've also dedicated a few minutes at the end of today's presentation for Q&A. Please feel free to drop your questions in the Q&A function in your Zoom toolbar at any time during the presentation, and we will get to as many questions as we can. I do encourage you to be as specific as possible when sending those through. Please feel free to include an example or reference back to a particular area within the presentation to better assist Jeremy and Frederic in thoroughly answering your questions. But without further ado, I would like to introduce our speakers. Again, I'll begin with Frederic Dessy. Frederic is a medical physicist and has been working for more than 13 years in radiation therapy, delivering radiation treatment to cancer patients. He joined IBA 14 years ago working for the particle therapy business unit in charge of the proton beam dosimetry, integration of third-party systems, and patient imaging. Since March of 2020, he's been working for IBA Industrial's business unit as a product manager in charge of the X-ray solutions. Today, we also have Jeremy Brison, who's been working for IBA in R&D and innovation since 2011. Before joining IBA, he was a researcher in the field of physics and bioengineering for more than 10 years. In prestigious universities and research programs. He attended the Accelerated Management Program at Solvay Brussels School after his PhD in physics at the Université de Nemours and postdoctoral in bioengineering at the University of Washington. Today, Jeremy manages the product management team in charge of developing the industrial irradiation solutions and applications of tomorrow. Right now, I'm going to hand it over to Jeremy, who will be speaking first.
Hello everyone, this is Jeremy Brison from IBA, Director of Product Management, and today I'm very pleased to be joined by Frederic Dessy, our product managers specialized in X-ray solution, to discuss about X-ray integration. So as you can see in my talk, we had a great webinar a few weeks ago about the theory of X-ray. Today we will go into industrial solutions, and we'll have about 40 slides to go through all the details that are really important to prepare your X-ray project. So I hope you enjoy it, and I see you for questions in 40 minutes. So just to start, I will begin with a refresh from the last chapter. I think it's important to make sure that we all understand the principle, the fundamentals of X-ray before we go into the technical details. So I'm going to take a few minutes to summarize the work of the presentation of Frederic Stichelbaut last time. Then I will give you the introduction about the practical tips on how to design your integrated X-ray facility. Then I will give the mic to Frederic to review all the different solutions which are available. You'll see there are typically 4 solutions that we can use to make an X-ray project. And finally, I will conclude with a typical business case to show you how you can proceed to start your X-ray project and evaluate the feasibility of the project and the viability of the project. I hope you like it. Let's go, let's start. So, what did we learn the last time about X-ray? The first thing we learned is that X-ray are produced by Bremsstrahlung, a German word, saying that when you accelerate electron and you shoot at a metal, a thick metal layer, the electron will be deviated, slowed down by the atoms of the nuclei of the target, and will generate radiation, which are X-ray. So we limit the energy of the electrons to typically 5 MeV or 7.5 MeV to avoid the activation of the target. And so this is where the limit is set in terms of energy. And at these energies, you get a conversion efficiency. So you convert the electron beam power into X-ray power at a rate of typically 80 to 12%, 12% being for 7 MeV. But we will see that it seems to be a very low efficiency, but globally, the X-ray process is efficient, and we will see why during the presentation. So X-ray, when they are generated, exhibit a continuous spectrum of energy between 0 or 150 kiloelectron volts, very low energy, to the incident energy T0. But you see here in the plot that most of the energy, most of the photons have an energy which is around the one of the cobalt. And you see that cobalt has two rays here of fixed energy because the nature of the radiation emitted by cobalt is totally different because here it's a decay of a radioactive element. So X-ray, they are generated, they have an energy between 0, 3 MeV, a bit more here on the tail, and then they are neutral, so they can penetrate very deep into the material, and this is why we like it, these X-rays, because they can penetrate here, you see the curve compared to E-beam, they can penetrate 5, 10 times more that E-beam can actually in the material, so we'll be able to treat bigger volume with these X-rays. Finally, and very importantly, on the theory, the dose deposition is always done the same way. So being photons from gamma, from X-ray, or being primary electrons, in the end, you convert everything into secondary electrons, and those secondary electrons will deposit the dose in the product. So a photon is a photon. The way you will kill the bacteria, the bioburden, is actually the same for all these modalities. So it's more a question of distribution in the volume, but the nature of the radiation impact on the material is the same or very similar. Key messages also is that we need to optimize the X-ray converters. This is really what makes the success of an X-ray solution. So they've been optimized for a long time, and Frederic explained you that they've been optimized first to maximize the X-ray conversion efficiency, to optimize the X-ray field, the geometry itself, how the X-ray will be directed to the product, to reduce the secondary electrons in the product, very important to avoid a problem in the dose deposition, but also in terms of engineering, to optimize the cooling design of the target and the horn, and you'll see why it's very important, because you have a lot of backscattering during the process, and because 88% of the energy is actually lost in the conversion, you need to get that power out of the system. And finally, all that is done to maximize the reliability and maintainability of the solution. So Frederic showed you this nice target, which is a movable target made of a sandwich of tantalum that you see there, water, and stainless steel. So you see that the steel here will stop this secondary electron and prevent it to go to the product. And in the end, you have this beautiful horn here that you see. That's a 3 meters scan horn, X-ray, fixed only. So you see the tantalum will be here, the sandwich. You see all the horn here, which is a jacket of water, because all this needs to be cooled down. And this here in the back is a screen to prevent the secondary photons to be back onto the accelerator into the rooms around it. And so this is the 3 meter scan. You can also adjust the width here of the scan and the length, obviously. And we have a clamping system to maintain the tantalum sheet in place. So Fred also told us that the dose distribution can be calculated by Monte Carlo simulation. He showed us we can evaluate the D minimum, the D maximum, get the DOR, and from there get the throughput in cubic meter per hour. And what he showed us is actually the DOR is already 30% better than it would be in E-beam. So remember, the efficiency of X-ray was, yes, conversion a bit low, but here you already gained back some efficiency because the DOR is so much better than in E-beam. Fred showed us that in 3D you can calculate here using simulations the dose each spot. So you can place a dosimeter here. You see the edge effect. So this is the Z. So this is the height of the pallet. And you see that the dose will change on the length, on the height of the product, but also in the depth of the product. And so we'll calculate that in 3D. Here you see the dose in the double side product. So you shoot here one side, you shoot the other side. And for a product of 0.1 gram per cubic centimeter, you get a DOR of 1.3. but that DOR will vary strongly depending on the product properties, the width, the depth, the height, the density, the filling of the pallet itself, and also the conveying method and the beam scanning method. So already increases to 1.9 instead of 1.3, everything being kept the same simply because you increase the density, the average density of the pallet. Okay, we are back now to the fundamentals. We are refreshed our memory about everything we need to know. We can go into the details of the facility design. And I'm going to give you an introduction and then Fred will take over. So everything you need to know about an X-ray facility is here, shown on this 3D. Sorry if you've seen that recently. I've been showing this slide quite a lot recently. First, we have the Rodatron here inside the vault of the accelerator. You see the modular Rodatron, the beamline, and the horn inside the wall. That's the first thing we show. The second thing, very important, is the conveyor. The way you will bring the product in front of the beam is extremely critical to make an efficient X-ray system. That's what Frederic will explain. Here we see a simple double side. So the pallets are moved into the maze here, move up and down here. They are rotated in the back. And so this is the conveyor. And as you see, there are many different technologies that you can use. You can even, if you like your conveyor provider for a gamma facility, for example, bring it to this solution and build a Lego with the two different elements and the other ones that I will show you. The third element will be the process control system here, where we have a simple software suite, which actually manages the Rodatron, the recipe, and the conveyor to make sure that you have the correct dose and the correct recording of the dose in the product. Then around that, we have the shielding. This is made of concrete. You start here, the radiation is emitted from the product mostly, and you go in all directions, and you need 3 meters of concrete to attenuate the X-ray to prevent people outside the bunker to receive those, and this is why we have this design. And also the X-ray can bounce on the walls, and this is why we have this maze that we need to protect the people in the facility. Finally, the technical rooms where we have the water groups, one for the Rodatron, one for the magnets and the RF, one for the X-ray target itself. We have some room here for the dosimetry room. We have all the electrical supply. You see here the 3 big power supplies for the high voltage. You see the power distribution cabinet as you would have at home for the electrical wiring, and some control cabinets. And this is all you need to make your facility. Last but not least, the building safety, a system that prevents people from entering the Rodatron vault or the treatment area when the beam is on. And also, finally, if you need to move thousands of pallets every year, you might think about having an automatized warehouse here outside the vault to manage to load the pallets, to prepare the pallets, to unload and to load the trucks on the parking. If we zoom a little bit into the details of this facility, the first thing, as I said, is the Rodatron. You see here a TT200 with all the magnets, the copper-plated cavity. This is for a 10 MeV. This is the flower that we know, where the name of Rodatron comes from. In the case of a TT1000 for X-ray, the machine is optimized for very high current. And you see that we don't have 10 passes, but only 6, actually. Here we have a special magnet 1, which allows a bigger current. So you see that thanks to this magnet 1, we can reach current up to 80 milliamps. At 10 MeV, it would be around 30 milliamps. So you see that here with the bigger holes and the big magnet 1, we can go to very high current. So this machine is really optimized for X-ray. In the back there, we have what we call a delay magnet. And when I'm going to click, you're going to see the change here. We stop this magnet, we start this one. It doesn't change anything in the optics. Instead, that the beam goes here and is now slowed down the cavity and exit at 5 MeV. And so this delay magnet gives you the opportunity to have 5 and 7 MeV. And this is actually the 2-energy Rodatron that we presented at last IMRP. Very important also, you see that the efficiency of the TT1000 is 55 efficiency percent. This is also the double of an e-beam system. And so that means that, again, you win some efficiency that you lost in the conversion. So again, you see that we recover the efficiency lost in the first slide, the physical limit of the process. Product handling is very important. We'll see you today mainly 2 different technologies, the overhead conveyor and the rollers. Both technologies are very valid. You can control the speed. They are modular. They are using modules that are used in logistics or automotive industry. It's just the underbeam, so the part which is in front of the beam, which is specifically designed for irradiation and sterilization because it needs to be radiation hard, which is very specific to our industry. But technically, all the modules are used somewhere else in the industry. We do, and it's very important to focus also on the uptime of these conveyors. We shoot for 98, 99%. When you combine the two systems, you need to have the highest efficiency and the highest reliability possible. So don't overlook this conveyor system. Finally, the Beagle will also be an important part of this integration. The Beagle is the brand at IBA for the process control system that you see there, the software suite. You see that you can track your product. You can also connect it to the ERP of your facility. Very important to be efficient. A lot of data logging, data tracing, fully flexible and tailor-made. So every project is really unique. And the reporting is FDA compliant. Few images to illustrate what I just showed you. This is the beautiful new TT1000 new generation. You see the cavity here, the same as a small Rodatron. You see the magnet one I was talking you about. You see the beam line here going straight. The horn is in the wall. You see that everything is pre-cabled in factory, so installation is easier and easier. You see the modular power amplifiers that we've been developing at IBA to simplify this RF system and make it more redundant and simpler to install. So this amplifier is actually the same for all Rodatrons. And the delay magnet also very simple here. So you see that really the innovation in this new generation of TT1000 is to make it simple, more reliable, and more redundant to have the higher reliability possible. The Beagle, just a few words about that. You see simply the production order here where you set up all the products, all the recipe, because the product will run for hours in the vault. So you set all the products, you choose your recipe, your beam, the dose that you need. Then the product is tracked in all the facility here. This is an e-beam example, but it would be exactly the same in X-ray. And you see that we can integrate, if you have some automation here, so these are robots that you can integrate. We have a button for dosimetry here, and many different interfaces that you can have. This is really a system that we like to tune to reach the desired functionalities of every project where we work on. Finally, monitoring is very important. Here you see the different parameters that the system can record: conveyor speed, the current in the beam, the scan width, the scan offset, the pseudo-parallel, scan length, the energy, and finally you get a dose, which has to be accurate, and you can record that in the reporting. Okay, now that we know everything about how to make a facility and the components, we can go into the more detailed process of X-ray and how we can optimize it. We have seen many times this year that, again, the mass thickness is very critical, the penetration of the radiation in the product. We have seen that for the choice that we have is between, for low density product, you will go for E-beam, and thin products for high density, we go to X-ray. But how do we do that concretely? If you take a box, I always show that the simplest way is to shoot it laterally. The problem is that the penetration of the beam will be low here. So if you want to increase the throughput, you have to stack the boxes up here, which can be complicated, and you have to do it manually, so that can be a challenge in terms of logistics. So what we try to do is to go from the top. This is what we do, top-down irradiation. So we put the box here, now we treat the larger side, and if we want to increase the volume, we have to put multi-boxes under the beam, and this is how we do the very high throughput E-beam. If you don't want to do all that, either manually or to use robots to palletize, depalletize, X-ray is the magic. We simply put this converter, we put the Rodatron and the horn laterally, and we treat the pallets directly. This is the short side, moving on the direction of the conveyor, and we treat the longest side to increase the throughput as much as we can. But how do we treat the product actually? We have 5 different ways to treat this product. The first one is the simple, what we call the double side simple overscan. So here we scan actually larger than the product, and we have some overscan there because we know that we have some edge effect. And the larger you scan, the better you actually have a dose distribution. But we know that if you overscan too much, you waste some energy and some throughput. So the second thing we can do is to put the product in front of the beam to reduce the overscan and to rotate the product. That's nice, but it takes some time to make the product in rotation and to go from one pallet to the other. And the third one would be to actually modulate the beam here. So you can actually slow down the scanner here and accelerate to have a modulation of the beam, to have the perfect dose distribution. And in that case, you can also reduce the overscan. So these are the simple double side, one level, as we call it, treatment. The second one, which has come from the gamma industry, it has been industrialized by Hans Hartmann and his team, is to actually overlap the product. So you have two products, one on top of each other. You scan in the middle. So you see that you don't have here any overscan, so no waste except in between the product. And then you swap and you rotate the product as much as you need to have the dose uniformity that you need in your product. That's a very smart way to do it, and I'm going to detail that a little bit later. And the last one is to do what we call the multi-row. So we take a Rodatron again, we scan the first pallet, and because we know that the photons penetrates quite deep in the material, we can put a second pallet in the back and use the radiation, and Fred will explain you the advantages of disadvantages of this solution. So you see that, you say, okay, that looks quite complicated. What should I do? Just to give you some hints here, you see that most of the time, people in the industry choose between these two solutions, either the first one, which is the double side irradiation one level, or the two level double side here, what we call the four sides, for a more flexibility. And that's what really Fred will explain you today, is the differences and the practical aspects of these different configurations. Just a quick zoom on this four side because it's not very intuitive. Again, you shoot here, you see you do the first phase of the product here, the bottom and the top of the two pallets. Then you do a rotation and you do the other side. Finally, you swap the pallet 1 and the pallet 2, so invert it and you redo the middle part. And you do again a rotation, and then you have this fourth side treated by this technology. And you see that the advantage, if you look at the dose distribution, is that on top you get these red curves. When it goes to the bottom, you get the blue curves, and in the end, you have this beautiful flat dose in the product. And also, what is really remarkable with the fourth side is that it's very independent of the different pallets that you have. So each pallet is treated almost independently from the other ones. A summary before we go to the practicalities with Frederic. This is the last slide of Frederic Stichelbaut a few weeks ago. You see the summary for 7 MeV. We have the double level two-sided in red. We have the one level two-sided in blue, and we have the one level rotating in green. The density is there and the DOR is there. You see that for medical device, the best result in DOR is obtained by the two level two-sided. Then you have the one level two-sided, and the rotation starts to be very efficient at mid to high densities. And if you convert that into throughput, you see that thanks to that better DOR red, the two level has a throughput which is 20% higher than the single level, and then the single level is there decreasing with the density. And finally, the rotation is a bit lower in terms of volume because you have the time to make the pallet turning in front of the beam and moving to the next one. Now I'm going to give the mic to Frederic to go to the different solutions and the specificities of the different solutions, and I will get back to you in a few minutes. Thank you very much.
Thank you, Jeremy. So now I will go with you through the different specificities of the different solutions that Jeremy mainly presented. So first of all, we're going to speak about the different throughput and what we can reach with the different solutions. So to be able to compare the different solutions, we take some hypotheses. And so to make those hypotheses very clear, here are those ones. So we are speaking about a minimum dose on the product of 25 kilograms. We are also speaking about Euro pallet of 80 times 120 times 180 centimeter, then this is cubic centimeter. We are speaking about treating the different products during a full year, so meaning 8,760 hours a year. And as Jeremy mentioned, we will have some downtime on the system. So we took those one into account, meaning that we took 3% of Rodatron downtime and 3% of conveyor downtime for the system, so for the hardware system. We know that there are also dosimetry and different operation of loading and unloading and different gap between the different batches. And so those one has been taken into account as well. We are using the maximum beam power available, so meaning 560 kilowatt of beam. And finally, with the different system, we took the hypothesis that the distance between the different products is minimized and that the maximum speed of the conveyor is at 3 meters per minute. So knowing all those hypotheses, we will look now at the different solutions. So for the first solution that Jeremy mainly presented, so we have a one-level, two-sided solutions. So you can see here how the product will be irradiated with some overscan. You can see that the blue beam, the beam represented in blue here, has some overscan on the product, over and under the product. And so with this system, we will mainly reach 100,000 cubic meter a year. And this is for product density that are close to what we consider as being the density of the medical device for 25 kilogram of minimum dose. And with this solution, we reach a DOR of around 1.8. So for this system, we will have the possibility to treat the product with a horn of 2.2 or delivering a beam of 3 meters. And the typical overscan we can have there is around 20 centimeters. So this means that you can treat different pallets of product of either 1.8 or 2.6 meter, mainly in terms of product 8 that can be treated with this system. So this system will require, as you see here, one level conveyor, and the total volt 8 will be around 3 to 4 meters. It depends also on the horn you have selected. The treatment area you will need is around 900 square meters. So now when we look a bit more closely to how the product will be treated, you see here that we will have the product that will enter the vault by this line. Then it will have the possibility to be treated in a loop in front of the beam here, where we can also have a product rotation out of the beam that will be located here. And we also have optimized the shielding so that the footprint is optimized and that we have at the exit of the vault dose rate that is compatible with the maximum dose available allowed for the public area. We have also worked on the optimization of the distance between the product and the horn. As we can see that the closer we are to the target, the higher the dose rate will be. And so this means that if we have products that are at a distance that increase from the target, we reduce quite largely the dose that the product will receive in a certain amount of time. And as I mentioned, we have also an internal loop that allows to have a multiple pass for the product in front of the beam. So now when we look at the installation itself, so that installation we have made one in the US and the other one in Europe. We can see here in the US that we have two different targets. We have a target for the beam of 5 MeV and the target for the beam of 7 MeV. And this is with a roller conveyor. And for the other installation that we see here, we have the horn that is located here, and we have a tote conveyor that is mainly bringing the product in front of the beam. So the take-home message from this configuration is that we reach a medium DOR, which is typically of around 1.8 for the medical device density. We have a treated volume for the medical device density that will be around 100,000 cubic meter a year. We have a quite simple conveying system, and the capex will be what we consider as medium, mainly due to the fact that you have a simple conveying system and that the shielding is not too complex and you don't have too high building for this solution. So now let's consider the second solutions that Jeremy presented. So mainly the two-level, two-sided system. So we can see here that we have the two level of the product in front of the beam. So in this case, we do not have overscan anymore. We have what Frederic Stichelbaut called underscan, and that Jeremy presented a few minutes ago. With this system, we effectively have an increase of around 20% of the volume you can treat a year. And what is also really interesting is that you end up with a DUR that are lower than the one of the previous system that I just presented. You can see here that we still have the possibility to treat with the horn of 2.2 or 3 meters. This mainly depends on the product you would like to treat. We, as I mentioned, we have no overscan, and we can have some vertical gap between the product. The conveyor will be a two-level conveyor system, and of course, the vault will be, in this case, the vault 8 will be around 7 to 8 meters. The treatment area will be mainly the same as the previous one, around 900 square meters. So now, if we look at the different possibility and the different conveyor type, we can see that we can have either a two-level roller conveyor. What is interesting in that aspect is that we can have very short distance between the product. We can have a quite good flexibility in terms of pallet dimension, in terms of length and width, mainly if you need to combine European or US pallet. One of the drawbacks is that the position of the roller here and the position of the roller there is fixed. So meaning that if you have pallet of different height, you will have some gap that will be created between the different products there. And another drawback of this system is that you have a lot of rollers, you have a lot of motors, and to be able to shift the product from the level low to the level up, you need to have different lifts to be able to handle those pallets and to make those kind of flipping from the lower to the higher part and from the higher to the lower part. Now, when we look at another solutions, what will be a tote solution, you can see that we can have, due to the parts that are present here in the tote, we can have a larger gap between the pallet. We can have very high flexibility in terms of product height into the tote. I will come back to that in the next slide. And what is really interesting, and this is what we are looking for, is that the system is very simple on the mechanical point of view. We have only one motor, one chain that drive everything, meaning that we can have a very high reliability of this system. And we have also a gamma experience with those systems, and those systems are in use in gamma since years and years, 13 years as far as I know. So now let's have a look at the tote system. What happens if the pallets are not full? So we can see here that we have the roller system. The rollers are represented in green here. And we have two full pallets on the system. So now we can have a pallet that is not full. And we can have another pallet that will not be full. And so we lost some space here. So this means that if your beam is treating this product, you will lose some beam and you will effectively lose some throughput due to that. So now let's have a look at the tote system. So the tote system with the pallet fully loaded, okay. And now what will happen if the pallet is not fully loaded? So we have one pallet put there. We have another one that will be put, of course, at that position. In the tote system, what is interesting is that we can design the tote system so that the pallet can be concentrated in the middle, meaning that the height of the beam can be reduced and so we not lose beam in air while we will deliver the dose to the product. And we can also put the different product and the different pallets together, so we can still make a full dose out of the product. And so this is something we have currently patented, and we are now waiting for the patent for this solution. So let's see now at a bit of the process optimization. So Jeremy mentioned that we have also to look at the what can happen outside of the room. So first, let's focus on the treatment room itself. So we will have a continuous motion of the product in front of the beam, so to avoid to have gap between the product and ensure a good throughput for the system. We have a two-loop system. This has some advantages because we can have there the product that can still go in front of the beam in case of an issue out of the treatment room. And we have also the possibility to have multiple paths for the product in front of the beam. We have an out-of-beam rotation that is available here. And so we can make some rotation of the beam of the product out of the beam. And this is to optimize the dose distribution, as Jeremy mentioned earlier. Now, if we look at what happened outside of the treatment room, we can see that we can have an automatic pallet inversion here. So the product will mainly enter into the vault in this direction, follow this line, being treated here, have the multiple rotation, then go out of the vault here, and we need to flip the product because we have a two-level system, and the product will be flipped here and go back into the system. So you see here a first loop, and the second loop is the one in front of the beam inside the vault here. So we will also have an optimized reliability of the system. We can have two different motors that will be redundant. So because this can be one single point of failure. So if we have redundant motors, that means that we are covered in that point of view. We can have automatic cleaning and lubrication of the system. We can also have an integrated maintenance. So this means that we can have the toad that will enter here, that will be maintained and go back in the loading area. And so there we can have a connected integrated maintenance into the system. We can have, as Jeremy mentioned, an automatic load and unload of the product. So this means that you can put the different, you can charge here all the different pallets you will have to treat for the week, and then the system will just automatically load those one and unload those one, and you can treat 24 or 7 days a week. You can also, in case of issue, sync to a backup system, so to make manually load, manually unload, and manually pallet inversion. So, a take-home message of this solution: the DUR is optimum for the two-level system. Typically, we can reach up to 1.5 for medical device density. You have a very large volume that can be treated. That's the largest one we can have. The conveyor, you have the choice between either a roller conveyor, which is more effective in case if you have the pallet of different size, and the toad will be mainly optimum in terms of system reliability and will be most effective in case of different pallet mixed. And finally, compared to the previous solution, the capex will be a bit higher because you have a two-level conveyor system and you have a higher vault. So let's look at the solution 3. So one level, two-sided, multiple row system. So we'll see here that we have multiple row of conveyor in front of the beam. So with this system, we effectively reach quite an interesting throughput, and we reach theoretically a quite good DUR. So now let's have a look at the practical aspect out of it. So we will have a horn of 2.2 or 3 meters. We still have a typical overscan of around 20 centimeters. And we will use what we call the pass-through beam. I will come back to that in a few seconds. There we need to have two lines in front of the beam, and this will require to have some complex scheduling. I will come back to that, and we'll need to have quite large batches to really take all the possibility of the system. So the footprint is a bit higher because we have two lines in front of the beam. So now let's look in detail on how this system is mainly working. So we have here the beam. We see the different depth dose that you can have. So I put the first pallet in front of the beam. Okay, my pallet is here. If I have a product of 0.15 gram per cubic centimeter, 120 centimeters, this represents 18 gram per centimeter square. So the beam will mainly, so the product will represent 18 centimeters of water to be treated. So this means that effectively you have some remaining beam that is available there. So I can put a second pallet there. Interesting, yes. But then you need to flip the product. And what will happen if your product 8 is not the same? What will happen if the density of the product is not the same? This will have a dramatically impact, of course, on the dose distribution, because there you can see that the dose will not be, in this case, you will have a dose that will be the one on the green for the first pallet, but on the top here, you will have the same green dose distribution there. And so this gives you very strong constraint in terms of pallet size. So all the pallets must be the same in terms of 8. You need to have a perfect synchronization between the first line and the second line of the conveyor line. If you have a gap between the different pallets and that is not aligned on the same way, you can have some old or some maximum or minimum dose that will be created. You need to have very large batches to ensure that you get the maximum out of those distribution. And finally, you completely lose the flexibility of what the X-ray system can offer you, because you need to treat those large batches and you need to wait for those batches to be treated before having another pallet to be treated into the system. So the take-home message that we would like you to have is mainly for the DUR, you have a risk on the dose accuracy, because you need to have a very good conveyor synchronization and the pallet mix need to be really under control. Of course, you can treat quite large volume, but this one required large batches of product to be treated. The conveyor need to be really well synchronized between the two different lines in front of the beam. And in terms of CapEx, it will be higher compared to the one level solution, one line. The footprint is larger and you need to have conveyor with two different lines. So now we will reach the fourth solution, so the one level rotating. So for this one, you need to pay attention because there is some change in the hypothesis. Because as Jeremy mentioned, we have here, we are looking at another density. So this is more a density that will be the one for the food. And for the food, the dose is much, much lower. So we are more at 0.4 kilogram as minimum dose. And so with this one, we can reach very, very large volume. Mainly the limitation is not the one in terms of power or in terms of treatment hours. It's more the maximum speed at which one your conveyor can go to treat and to transport the different product. You still have the horn of 2.2 meter or 3 meter and typical overscan of 20 centimeter. You will need to have one level conveyor with a rotation in front of the beam, and the footprint will be typically around 900 square meter. So some example of installation. So we can see here an installation where if we look closely to what happened in front of the beam, as we know that the product will need to rotate in front of the beam, we need to move the product a bit away from the target, as the pallet is not square. This is a rectangular pallet. We also know that the food is a quite seasonal treatment that need to be applied. So you can even think to have a double line in front of the beam, a line where you will have the product that will rotate in front of the beam, and a line that will offers you the possibility to treat like the one level, two-side system with a 180-degree rotation out of the beam. So this is more a system that will be high density focused, mainly for the food. So the rotation in front of the beam will ensure a high, very good density, very good DUR for the high density product, and the translation can also ensure a good DUR for the low density product. So the take-home message for the rotating will be that the DUR will be really optimized for the high density, mainly focusing on the food. The treat volume can be very large. The limitation will mainly be due to the conveyor speed. Low power will be needed. The conveyor, you need to have a rotation, of course, in front of the beam. You can have two possible solutions, either the toad with two lines to optimize the throughput, or with the roller. For the roller, it's more complex to have a two line in front of the beam. And in terms of CapEx, it will be lower, mainly to the low power that you will need to treat your product. So now I will let the word to Jeremy to come back on the X-ray business analysis. Thank you.
Okay, thank you, Frederic, for this very nice description and detail of the technical solution available. To conclude this talk today, we'll spend a few minutes on the business case example for the X-ray, and for that we would like to thank Candice, who is our sales manager located in the US area. She provided us with the model and the numbers, so if you have any questions, detailed questions, don't hesitate to contact Candice, and we thank her for providing the numbers. So you know everything now, huh? So we have this Euro pallets, a large volume, we have the dose, we have on the left side, as you can see here, a volume that will be ramped up. We'll start with a few thousand cubic meters, and after a few years, we want to be at full volume above 100,000 cubic meters per year. You know the footprint, and in this case, we will take manual loading and unloading in the numbers, and we will run these numbers into a business case tool to see how what will be the price actually of the treatment that we want to apply to the pallets. For that, we took a typical TT1000. We started at 300 kilowatts, and we would increase the power as much as we need to reach the full volume after a few years. You see that the consumption has been taken into account. Obviously, we have 1.5 megawatts typically for Rodatron, the conveyor, the secondary cooling, and all the equipment that you need in the facility. With that conveyor, we need to move 8 to 9 pallets per hour. So keep in mind that we might need automation on top of what I will show. And finally, you see the plot here of the shifts and the hours that we run the system. So you see that we take some hypothesis in yellow, the operating hours that will increase from 1,000 hours per year to 7,000 hours per year. You see the beam power in blue on the right side, and you see that we will start with 2 operators, 1 shift, and we will increase that to 3 shifts the remaining years to make the full production, because to treat 100,000 pallets, you need 3 shifts, more than 300 days per year. How does it look? You see that the CapEx, and that's a question that we have very often, is a bit superior to what we would have in e-beam. So it's between 15 and 22 million US dollars, including everything: the building, the land, the offices, the shielding, the Rodatron, the conveyor equipment, and all the engineering you need, process control, fire system, etc., etc. Then you have obviously the recurrent spending, the OPEX, that will vary from the 200,000 US dollars up to 2.7 million, including the cost of electricity. That again we took in our models. You have the labor here, the fixed cost as the insurances, the rent, etc., that we added to this electricity. And in the end, even if these numbers are significantly higher than the ones we have seen for the e-beam cases a few weeks ago, we see that the cost that we pay per product to be treated is around $44 per cubic meter, which is close to the $40 per cubic meter that we saw in the case in e-beam. So actually, as we explained, because it's simpler in terms of automation, because it's very simpler also to move the pallets, and you have a better DUR, in the end, the cost that you pay per unit is close to what we have in e-beam, and you see that after a few years you have already stabilized the cost. You see that if you pay now a bit more than $100 per cubic meter for sterilization, you have a payback in 5 years, and you have a return on investment which is above 20% on this project. So very viable X-ray projects, and don't hesitate again to that was an example, but to discuss with Candice if you want to fine-tune the numbers and for example adapt the cost of building and the cost of the land from your country. Now that you have this business case in hand, you want maybe to check if your product is ready for X-ray, what should be done to make it ready for X-ray. You maybe want to validate the hypothesis that we took in terms of DOR, in terms of volume. You can do that in one of the facilities around the world which have been dedicated to process validation and to product studies. The one we have close to Belgium is in Strasbourg, is our partners of Aerial. You see that we can do a lot of different things there, like for example, material studies, research. We can do a comparison between different modalities what we have done in the Neblo project, for example. We can make a strategy to transfer a product from one modality to another. We can do a detailed process qualification to see how it will be done in the actual facility. We can do a lot of Monte Carlo simulation to verify the hypothesis. You can be trained also, and you see there the picture from our partners, Trad and Ray Experts, that you can get online to be trained on Monte Carlo tools. And from there, you can really validate closely your throughput and the volumes that we have taken in the assumption. But we can do more. We can also optimize different accessories. We can verify the cooling condition, atmospheres, etc. Even if this is more for fundamental studies, it can be useful. And finally, last but not least, during the project, which will take 12 months typically to be out of the factory X work, you can be trained, you can test the different features like the PCS, you can play with the conveyor, and you can also learn about dosimetry. So very useful to start your project with one of these facilities in the world. They have very good ones in the US, in Europe. Don't hesitate to contact us. It's time now. Thank you very much for your patience. It has been a long talk to go to the conclusions and the perspectives. If I would have to summarize my talk and Frederic's talk in a few seconds, I would say that X-ray now is a routine and mature technology. You've seen that integration has been studied in detail. We have more and more projects. 2021, 2023, we'll see a lot of new X-ray projects emerging all around the world. So it's really different from what it used to be. X-ray is today really routine. We have seen that at lower cost and footprint, you can start with the simple double level. It's the simplest way to a single level, simplest way to do X-ray integration. It offers decent DOR and already very good volumes. If you want to increase a little bit the complexity to have more flexibility, better DORs in a higher volume, we can go to double level integration. It's really the more versatile solution. And finally, once you are convinced that you have found the right solution for you and what you want to do, you can get your project started right away by doing a detailed business case with our sales team or a product study at our facility at Aerial. Thank you very much for listening, and let's go to the Q&A session. Just before that, now on the slide, you remember that we already had 6 webinars so far. There will be one more coming in June about X-ray technologies. This will be about the new technology, the advances that we have in the product itself and the process. And so I'm looking forward to meet you again on this new webinar on June 17th. Thank you very much for your attention.
Thank you so much to our wonderful IBA presenters who I'm going to invite to turn on their cameras and unmute to come on the line to take Q&A. At this time, I also want to launch a poll for our attendees. We want to get your feedback on today's presentation, so I'm going to launch that right now. If you wouldn't mind taking a few seconds to come to your computer screen, I'm just going to leave this open for a few more seconds, but again, we'd like to get your feedback. So please do enter in your poll questions if you found the webinar insightful. Did the presentation cover the information that you had expected? Did you learn something about the different X-ray solutions after viewing? And was there anything else you felt the presentation should cover? Going to close this in just a few seconds. Jeremy Brison, Frederic Dessy, and Cody Wilson of IBA, welcome. Thank you so much for being here. And thank you again to everyone voting. Going to close this off in just about 3 or 4 seconds. So again, please feel free to drop your stats in there, and closing the poll now. Gentlemen, thank you again for being here today and for all of the information. We certainly appreciate that. I want to answer, or I'm sorry, begin with a question very quickly here. And I believe this first question is going to be answered by Jeremy. Jeremy, can you pulse the beam with the TT1000 in order to reduce electricity cost?
Can you hear me, Brooke?
I
Because
can
don't
hear
see
you, yes.
myself. Okay,
Yes.
because I don't see my camera. This is a good question. Actually, the pulsing mode, yes, it's possible to do it on the TT1000. So physically, nothing prevents it to be done. But in fact, because we need the maximum power of the machine, we need the full power, the full possible beam, and 100% of the time. So if you would need to run the TT1000 at half power, you could run it technically pulsed at 50%, but it doesn't make sense in terms of processing because you need a high power all the time. And also, what we try to do when we pulse is actually to take advantage of the fact that when the beam is lower compared to the DRF consumption, we actually pulse DRF to save some energy. But in this case, the beam is 5-6 times more powerful than the RF system, so the savings would be very low if we pulse the TT1000. Still, the pulsing is very useful to tune the machine. For example, you can do very short pulses at very high intensity to tune the optics, and that's good because you can do all the qualification at a very low power, very low consumption, and also reducing the risk to damage the equipment if you have some optics issue. And so it's a very useful tool to pulse those machines, to be able to pulse those machines. So we use the technology that we did for the smaller machine is useful, but not for production.
Thank you so much, Jeremy. Moving right along, and this question is for Fred. Fred, would there be an influence in the double level if the pallet height is not at its maximum?
So as Jeremy showed in the presentation, you can see that the pallets is mainly treated as they were alone on the system. So no, you will mainly have there no influence if the pallet height is different from the optimum height of the pallet. So that will be quite interesting, of course. This is one of the points that is really interesting for this system, is that the pallets are quite independent one to the other one in terms of height. What is important is to have density for the two pallets that will be one on top of each other, that will be close in terms of density to ensure that we will have the good dose distribution there in the pallet. But that's the one of the constraints for a pair of pallets that will be one on top of each other. So that's it.
Thank you so much. Appreciate that perspective. Another question for Cody Wilson of IBA. Cody, you said that I hope I'm saying this right, photon is a photon and that the dose is a dose. So why do we see differences between E-beam, X-ray, and gamma on some products?
Yeah, that's an interesting question and gets into the subtleties. I think the mission there is that largely, when they say that a photon is a photon, dose is dose, the ultimate effect ionizing radiation has on materials is very similar. We can find subtleties in certain material effects, but the effect on the materials and the microorganisms is largely the same. And in the end, all the modalities you're talking about, deposit, their energy with electrons. Either in the case of electrons, it's directly with photons, it's through ionization. But there are some key differences that lead to what applications we can consider with these types of radiation. The electrons are charged particles and they interact via Coulomb scattering, so it limits their kind of characteristic penetration depending on what energy electrons you use. And then the photons are neutral particles, so they penetrate further into the material and let us get better DURs for the same amount of material that allows you to consider larger applications. And in the question between X-ray and gamma, what would be slightly different there is that the gamma emissions are monoenergetic at two characteristic energies, 1173 and 1332 keV, and the X-rays are continuously distributed all the way up to the incident electron energy. While most of those photons that it yields are lower energy, there are enough higher energy X-rays yielded that you can end up with some further penetration into the product that allows you a better DUR typically. But yeah, your question why there are some difference on material effects, it's very subtle. Largely, we see that they have very similar effects on materials, but they're in the case of specific polymers and everything, of course, care needs to be taken and product testing needs to be performed to make sure they're a match.
Thank you so much for that insight, Cody. Certainly appreciate that. Another comment that came through that I believe Jeremy is going to address. Jeremy, this attendee is saying, I imagine these systems are good for countries having world market access for their product, not for smaller producing countries.
And that's something we could not address today, but I'm glad we had this question because the last years, for the first time, I've seen X-ray project at very small scale. So I thought it would be only for very high production, very big service centers and global distribution, and that's what I thought before. But now, because the smaller machine have reached such a good maturity, I've seen some very interesting project at lower volumes. Below 10,000 cubic meters per year, with very high value products, where actually an X-ray case can be seen as profitable. So I would say, don't give it a try. Every case is unique. Every project is unique, and you could be surprised. That's what I would say. I think it's an interesting comment. I hope it gives some perspective to this question.
Absolutely. Thank you so much. Another question for our panelists. The volume seems to be lower than the values than I have seen before, which were more than 150.000 M3 range. Why do you lower volumes with your solutions? And Jeremy, I believe this question is for you. Let me know if you need me to read it back.
No, it's a good question that I understood. Fred could also answer to that question. So indeed, in the past, we have seen some references at conferences much higher than what we have seen today, the numbers of Frederic. And I think Frederic, in his models, is pretty conservative in the way that we took some margin on the dose, and we take the highest possible dose. When we see typical service centers, we know that the dose distribution in the products will be more variable. So you will have some packaging, for example, at lower dose, around 5 kilograms. We have some sterilization at 15 kilograms. And so when you mix up all those products, you can certainly increase significantly the total volume that can be treated by a center. So these numbers are quite conservative. Again, they have to be used carefully, and we have to go into the detail of the project to see what would be a reasonable number to hit once the center is in full production. Would you like to add something, Fred, to that?
Yeah, I fully agree with what you said. We took margin. We took 5% margin for mainly the minimum dose. We also took margin to take into account the downtime that the system can have, and we also took margin for the maximum dose, as you mentioned, and the dose accuracy. So effectively, that's something we were quite conservative when we presented those numbers, indeed.
Lovely.
Thank you, Fred.
Thank you both. No, thank you to you both. Apologies, Jeremy. And last question we have time here for, which is, I believe, is for Fred, a two-part question. What is the typical needed installation time for a complete system, and do you have a team that follows the complete installation?
That's an interesting question, of course. So the typical time for the system installation is around 12 months, I will say, from the time the system will be installed to the beam will be ready for the customer to start their center. And there we can, of course, provide some help to start the center. Another point is, yes, we have a complete team that can help you there. So we have effectively project manager, we have physicists that can help you on the IQ, OQ, and some of the PQ. So we have effectively work on that aspect as well.
Just Fred, because I'm not sure I understood clearly here, it's important. So the X work time to have the material ready and produced is 12 months, shipping. Mm-hmm. And then on sites, once the building is accepted, it's typically for X-ray 4 to 6 months, plus a couple of months for the PQ, the first product, and the ramping up. So that would be a total of 18 to 24 months to be to be up and running, right? That's,
yes.
Okay. Thank you, Fred.
That's what I mean. Yep.
Thank you, gentlemen. We're just about at time. Any final thoughts from our presenters today before I wrap us up?
Not on my side. Cody, you want to add something?
No, appreciate it. Thanks everybody for the great questions.
Lovely, lovely. Well, thank you so much to all of our attendees. We hope you found these courses with IBA informative. And of course, we will be in touch with details on further courses. And again, you can reference all of these materials on the IBA Industrial YouTube page. But thank you again to today's presenters, Frederic Dessy, who's the product manager, as well as Jeremy Brison, Director of Product Management and Innovation. And thank you so much to Cody Wilson for also jumping on the line to take some questions today. Again, for all of our attendees, I'll be in touch with a copy of today's presentation recording, but any further questions or comments for myself or the IBA Industrial team, please don't hesitate to reach out to me directly at webinars@q1productions.com. Thank you so much, everyone. Be safe and be well. Have a great day.
Thank you.
Thanks, Brooke.
Bye-bye.
See you. Bye.